Hello and welcome in another lecture of quantum computing. We have seen Grover search, we have seen amplitude amplification. We will see it as a black box again and see its application. And today's task would be to actually show, or this week's task would actually be to show that Grover search is optimal. You cannot improve it. And that has a philosophical implication. I will talk about it, but let's start with Grover search and amplitude amplification as an algorithm. What does Grover search do? It finds a special element, it finds a marked element in a list of n elements using only order, root and queries, which is very surprising. In a list, in the worst case, you might have to see all n elements to check if something is marked. But quantumly, you can do it only with how many queries? Root n queries. And indeed, this is not a very special phenomena. What we can do is something called amplitude amplification. What does amplitude amplification say? Given an algorithm with success probability p, right? If classically we want to repeat the algorithm and get success probability constant, how many times do we have to repeat? 1 by p, right? To go from probability p to constant, we need to repeat it 1 by p times. What is great quantumly is that we can only repeat it order of 1 by root p times. It's clear that 1 by root p is smaller than 1 by p. So there is a quadratic advantage. So anytime we have an algorithm with success probability p, we can very quickly get the probability of success to be constant. The things required is, one, you should be able to verify correct solution. Okay, so after each iteration your success probability is p, it will give you a solution. Okay, this is my solution. You should be able to say, oh, am I done or do I need to repeat it? That's one. So that's the, in some sense, that's the ability to know whether something is marked or not. It's equivalent to here having an oracle which says that my element is marked. It doesn't find the marked element, it tells me whether the element is marked or not. So we need to be able to verify correct solutions. This difference is clear, right? Verifying correct solution is much easier task as compared to finding the correct solution, right? So I should be able to verify correct solution, and second, there shouldn't be any measurements in the quantum algorithm because we really want inverse of A2. You remember one of the reflection we did by A reflection 0, A inverse. So we need the inverse too. Given a classical algorithm whose quantum version or a quantum algorithm where these two things are there, we can amplify very fast. You saw a lot of examples in the quantum walk case. Let's see another example. Okay, and the best part is here, we don't look at how it is done. We just use this amplitude amplification as a black box. But why am I calling it amplitude amplification? Once again, if my algorithm has a success probability p, that means my final state will be so these are correct solutions, or at the end of the algorithm, I will have a state like this which have some projection on the correct solutions and some projection on the incorrect solutions. If my success probability is p, what do I know about sin theta? Correct. Marked state or correct. Right? So how much this should be if my algorithm succeeds with probability p? Under root p, correct? So this should be under root p, right? And this algorithm, if you look at it inside, it goes like root p, then increases it a bit using rotation and gets this root p to constant. And constant amplitude means constant probability of success. This is very similar to the classical case where instead of amplitude, I amplify the probability of success, right? Again, the message is amplifying amplitude is much faster than amplifying probability, okay? So let's see an application. This is all I am going to say about how amplitude amplification is done, but once you know this, let's try it on this problem called element distinctness. We did this problem for the walk, but let me remind you once again. I have an input which has n parts. I am calling them x1, x2, xn. I am not calling them n bits. I am calling them n parts because each of the xi is some element from some range. Okay, some big number. Xi is in itself a big number. Okay, so I have how many big numbers? Small and many numbers. Okay, you can think of them as colors, you can think of them as names, you can think of them as big numbers. Given such n elements, the question is, are all these elements distinct or there exists a collision, there exists I and j such that xi equal to xj. This is what you want to decide. Simple question, correct? What are you given? You are given a black box, given I, it tells you what is xi. Okay, this is the quantum version of it. We have done this multiple times. If the classical oracle is this, we write the quantum oracle as this. Sounds good? So given I ask what is the ith index, it tells me the ith element. That oracle I have, and I have to figure out whether these elements are distinct. How many this I have written by one line, but there are a lot of qubits here. How many qubits are here? What are the choices for I? 1 to n. So log n, right? Similarly, this has to capture all possible answers from R. So how many choices are there here? R. So if you want to capture xi, that means how many qubits do I need? Okay, I am just saying it because generally this is 1 qubit in all the other oracles you have seen. But the problem remains same. I want to this you have seen multiple times. Doi, Jotsa, Simon, everywhere. I have an oracle and the task is to minimize the number of queries. And this is a good substitute for time. That's why we do it. So the problem is clear. So what do you think? In how many queries can you do it? Classically. In how many queries? I'm not talking about time. I'm talking about how many times do I have to look at the oracle? What is the dumb algorithm? I will query everything, x1, x2, xn. If I have everything x1 up to xn, I can check if two elements are similar or not. Right? I am not counting the time of comparing x1 and x2. I am only asking how many times do I have to query the ith bit, ith element. You understand the difference here? So that's why, since my input has length n, if I query everything from my input, I don't need to do any further queries and I can figure out any property of that input. And it is kind of clear in this case, I have to look at the entire input. Because if I, let's say, if I miss x1, probably the collision is happening at x1. That's why I can't give the correct answer. Sounds good? So my task is to improve on order of n queries. In the walk case, so you can also show that randomized also, that's the case. What we saw from a complicated algorithm was n to the 2 over 3. What I am going to say now, an improved algorithm, improved from here, a simple amplitude amplification algorithm which will improve ON. Okay, so you will see how we can apply amplitude amplification as a black box. Okay, in this walk also we did amplitude amplification, by the way, but this is much simpler. Okay. So the similar idea was used in the walk algorithm, but now if you think about this algorithm, what is the dumb algorithm? You say pick a pair I comma j. I will query xi, I will query xj if they are not already queried, and see if xi is equal to xj, right? But this seems slightly expensive in the sense that I have to re-query xi, just keeping two elements, querying them, and then if I want to check another collision, I have to check another pair once more. Instead, it might be better that I collect a bit of elements and query them at once. Clearly, I don't want to query all n elements. I don't want to query just two elements. Let's say I query r elements. Okay. So my first step is I know the values. So I pick a random subset R. So this is, let's say, R is a subset of 1 to n. These are R positions, small r positions. I am going to query everything. So I can clearly check if there is a collision here because I have all the values. Correct? Now, okay. So now I am asking, I am hoping that with high probability, wherever there is a collision, one of the element is here and one of the element is here. Okay. Clear? Again, I have to find out, this might not be a very successful strategy, but my strategy is very simple. I check these R elements, remaining things I don't know the value of, but then I want to see if there is a collision between some element here and some element here. So how many queries do we need to do that? That's the question, right? So what is second step doing? Is that clear? It is checking if there is a collision between R and n minus R. Is there an element I here and an element j here such that their values are the same? This is step 2. In the second step, we have to do sum. How many? That's the thing we will have to figure out. That's where I will show you an advantage. Classically, if I want to see if there is a collision, I will query everything here. Correct? Now, but the purpose of the step 2 is clear. I want to check if there is a collision between an element here and an element here. Okay? How many queries do I need to do this? So, this is my simple algo. Okay. Let's define an element to be marked. So, do you want to call this something? Let's call this set S. Okay. This makes sense? This definition makes sense. The way we want to do it, what do we want to do? If there is an I and j such that the value collides, I say that this element is special if it collides with something. This is the definition of an element being marked. Correct? In how many queries can I check whether an element is marked or not? In this setting, yes. In how many queries can I check if an element, a particular element here is marked in that way? The definition of marked. Single query. If I just have the value xj, because I already have all the values here. So even if I have a single, if I want to check whether j is marked, what do I need to check? If this value is equal to this value is equal to this value is equal to this, so on and so forth. But all the values of this are already queried. This is the advantage. This is why we spent our queries in step 1. So in just one query, I can check whether j is marked or not. Is this point clear? So, observation. Did I make myself clear? If these R values were not available, then it would have been a difficult problem. But I have already queried everything here. Correct? Then if I want to check if j is marked, I just query this value and compare it with all the values. Comparing it with all the values here does not take any query. It takes some time, but we are counting only queries. It's a randomized algorithm where we pick a random set R, do this, but for this time, this R will be the same for this instant. In different iterations of the algorithm, but in one iteration of the algorithm, I have fixed some R elements. I will find out its success probability later. But the algorithm is pick some R, capital R, which has small r number of elements, fix it. Query everything here, and now I want to figure out whether there is a collision between this side and this side. It's the same thing as when we had n elements, we picked one element and checked if it is marked or not. Right? So we found out the success probability of that algorithm. It was 1 by n, right? Similarly, now this is a randomized algorithm. What is the randomized algorithm? Pick a subset R of size R. This you are doing randomly. Then you are asking, is there a collision between this and this? Okay? And is there a collision between this and this? That complexity we are trying to analyze. I am trying to show you that by Grover search, I can improve this complexity between this set and this set. Okay, so it's clear that this thing is marked. I can check with one query because then we will be doomed, because then we will spend all our queries here. So that is why I have kept R as a parameter. What R to choose, we will decide soon. It will not be 2, it will not be n. It will be somewhere in between. So that's the whole point of this. Okay, but if I have everything here, then to check if this value is colliding with here, I just need to find out this value. So one query, right? Now, how many elements are here? N minus R. To find out if there is a marked element here, how many queries do I need? There is a set whose size is n minus R. I want to find out if there is a marked element there or not. Yes, that's the Grover search. That is written there. That is why I am saying think of this thing as a black box. You have a list of n minus r elements, correct? You want to find out if something is marked or not. What is the cost? So the cost of step 2 is square root n minus r multiplied by cost of checking if something is marked, which we know is 1. So then since r is going to be much smaller than n, it is going to be like n to the power 2 by 3 or to the 3 by 4 n to the half. This is approximately, I will say, square root n. Again, there will be O of r, O of root n for simplification. I am not considering those. The same analysis will work. You see that, right? If my oracle to check if something is marked took 2 queries, right? So then I will have root n minus r calls to the oracle which checks if this is marked, and the oracle itself will take 2 queries, so it would have been 2 times square root n minus r. That's why to check if something is marked, how much time do I need? How much cost do I need? Square root n minus r multiplied by cost of running my oracle if j is marked. Thankfully, that cost is just 1. That's why this is square root n minus r. Okay, good. So this is r, this is square root n. This is my simple algorithm. Yes. So now I want to find out what is the success probability of this, right? And then I can apply amplitude. Okay, so tell me what is the success probability of this? It's a simple question. The worst case would be when there is just one collision, right? So let's say xi equal to xj. Out of n elements, I pick a random set of r elements. What is the probability that, so the failure probability would be when both of them lie here, right? So what is the success, what is the failure probability? Failure probability is when both ia comma j are lying here. See, the total sets are n choose r. Correct? What are the bad cases? Correct? Right? Sorry, once more. So this is a simple probability question. This has nothing to do with quantum. Simple point is, suppose I have 2 indices I and j where xi is equal to xj. Now I pick a random subset r here. What is the probability that both I and j land here? So in how many ways can I choose a r size subset? N choose r. If both I and j lie here, that means I will choose this r from n minus 2 elements. This is my failure probability. This is my success probability. You can check r by n. Okay. So then, what was the complexity of this algorithm? R plus root n. Correct? how many times do I have to repeat this algorithm? If my success probability is this, how many times do I need to repeat this algorithm? Except Akshat. 1 by root r by n. This is P, right? So this is going to be my total complexity. This is because of amplitude amplification. This is cost of running. Right? Again, I am applying now this as a black box. Correct? There is an algorithm which finds the collision with probability r by n. I want to make it constant. That means I want to run this algorithm square root n by r times. Each iteration of the algorithm will take this much queries. Divyansh? Fine, right? You have an algorithm which you are running this many times, but the algorithm itself has this cost, right? So the total cost is this. When is this optimal? For what r? So now I will choose r so that this is the best. This is minimum. Exactly. So this is best when r equal to root n. So a simple application of amplitude amplification has improved your complexity from order n to n to the 3 by 4. So this is a nice tactic. You create an algorithm whose success probability was actually pretty bad, r by n, right? But then we can use amplitude amplification to get it to constant very, very quickly. Right? So we will not worry about this is a classical algorithm which can be turned into a quantum algorithm. Right? So all those we won't worry about. We have a quantum algorithm which has a success probability this, we can make it quickly, right? So there is an informal description of this algorithm which succeeds with n to the 3 over 4. You don't have to say, okay, I will apply this gate, that gate and everything. What is the algorithm? You will just say, oh, look at this algorithm, it succeeds with probability r by n, I am going to repeat it this many times by amplitude amplification, that is good enough. Right? Then someone who knows amplitude amplification can take it out and figure out what is needed at every step. How many header modes are needed? You have A inverse, but these many queries will be required. Sounds good? So even if you can't prove amplitude amplification, you can use it in your application. Okay? If you have questions about this, I would be happy to answer them after. But this is the message which I really want you to get. Okay, there are techniques which I have described using rotation, so you have the ideas of why Grover search works, because you are amplifying amplitude, which you can do by rotation or 2 reflection. But more importantly, using them as a black box, this is done very, very frequently nowadays. You have a problem in protein, you have a problem in search, in finance, you have it in optimization. As soon as you realize it's basically a search problem, you start thinking about Grover search or amplitude amplification. And if you think about it, Grover search is just a special case of amplitude amplification. What is the algorithm A and what is the probability? Sorry? The probability is 1 by root n. 1 by n. What is the algorithm? No. It's a very, very simple algorithm which you are amplifying. Wait. Amplitude amplification, Grover search is amplitude amplification of a very, very simple algorithm. What is the simplest algorithm if you want to search in a list of n elements? And check if it is marked or not, right? What will be the success probability of that algorithm? 1 by. That's what you are doing. What is this algorithm? The probability of success of that dumb algorithm is 1 by n. I can make it constant by running it 1 by root n time. We know quantumly I can do it in one query. This requires just one query. Right? What amplitude amplification is saying is that this algorithm could be much more difficult. It might use the structure of the problem, it might be much more complicated, doesn't matter. Still, I can amplify this probability much faster. Okay, this amplification from P to constant is really not dependent on A. Okay, if A is nice, then I can quickly go from P to constant. Yes. Xi. XOR Xi, yes. Set of two elements. Oh, B is not a bit now. I clarified, right? It has log R things now. It is giving you complete Xi, right? My oracle is now where every I gives me complete information about Xi. Remember when I made the oracle, I said, no. Okay, so let me first understand there are n inputs. Each Xi is log R bits. Here, this Xi is not one bit. This is the entire Xi log R bits. It doesn't allow me to check collision anywhere. It just tells me what my Xi is completely. Color blue or something, not the first bit of it. Okay, and generally this oracle and the oracle which gives you one bit of the input are the same because they are just differentiated by log R many, and log R we can skip. Okay, so we have assumed this simple oracle which gives me complete Xi. Okay, so now things are clear. So that's why I said this is log n qubits, and this is